Dr. Jessica Liu for her presentation, Stars Born in Extreme Environments.
Thank you very much, and it's a pleasure to be here. So I've given a number of these lectures before, but my favorite lectures to attend as an audience member are those where I can raise my hand and ask questions in the middle. So I want you all to feel free to do the same. I think I have enough light here that I can see if you wave vigorously, and feel free to shout those questions out. Don't leave them until the end. All right, so today I want to talk a little bit about how stars are born, but not a star like the sun. We'll talk more about stars in extreme environments. But first, I thought since we're all here in Hawaii, we should show a real advantage of being in Hawaii is the beautiful night sky. I come from California and Los Angeles and Northern California, big cities, and this is just not something you get to see there. This is a spectacular view of the Milky Way as seen from Mauna Kea, and you can see the two Keck telescopes there. So what are we actually looking at when we see this wash of bright light and this dark streak that goes across it? What are we looking at when we see the Milky Way? Well, we're seeing the galaxy that we live in, and that galaxy is a flat, disk-like structure with spiral arms in it. And here we are, our solar system, located way out here on the outskirts of the galaxy. It's a relatively lonely place where the sun was born and where the sun has lived and where the sun will continue to survive for the next few billion years. And you can see this in this artist's conception. Of course, we can't actually see the galaxy this way. We just see that streak. But in this artist's conception, here we are out here. It's relatively sparse. We have our nearest neighbors about 4 light years away. Whereas in the middle of the galaxy, it's extremely violent. Imagine if you put in 10,000 stars in the same space as our next nearest neighbor star here. The night sky would look extremely different. So I want to talk about how stars are born. And what we know about the sun, we know quite a bit about how the sun is born. But before we get on to that, I would like to say why I think star formation is important and why we don't know so much about it yet. So why do we care about how stars are born? Well, that's because stars are a critical aspect to almost every avenue and every area of astronomy that we study. Stars are key to making up galaxies. We have to understand stars if we want to understand galaxies. Stars produce black holes. So if we want to study high-energy phenomena around black holes or want to know what a black hole is, we have to understand how they came into being. Stars are also key, obviously, for planets. Planets wouldn't exist without stars. So if we want to know how planets are born, fundamentally we need to know how stars are born as well. So star formation is really a key component of all of astronomy. And what do we know about star formation? Well, like I said, we know a lot about star formation from our solar neighborhood. In fact, almost everything we know about star formation comes from our local neighborhood. This red circle here shows you all the region in which well-known star-forming regions have been studied for many decades now, and where we've formed models and physical theories of how stars are born. But as you can see, we are lonely and isolated, and when stars are born out here, they're lonely and isolated. So let's take a look at a couple of those nearby star-forming regions to set the stage. One of these regions is called the Taurus star-forming region, and here you can see the dark cloud that stars are born in. Here's a star that's forming here. There's another one right in there. Very isolated. One star, as it's being born, has basically no impact on the other stars that are being born in the same cloud. This star-forming region probably contains about 100 stars total, but it's very nearby, which is why it's so well studied, 450 light years away. In the same red circle as I showed you earlier, the next biggest star-forming region, it's a little bit more distant, at 1,300 light years, it's known as the Orion Cluster. And when you look at the Orion constellation, you can look at the Orion Nebula. That is a place of star formation, a region of star formation that's very well studied. In this region, there's about 2,000 stars, and you can see it's looking a little more active now. You can see all the gas and dust. And you can see some very bright newborn stars that are shining and influencing their environment, heating up the gas around it. And there you might say that these stars might be having an impact on new forming stars in the region. But still, it's relatively low-key influence. You know, you might get a little hotter, might get a little more mixed up, but not a whole lot. Okay, so that's what we know locally. But if we look further out into the galaxy, towards the center, or out into these very bright and dense spiral arms, what do we see? Well, here we see clusters that are quite spectacular. These are clusters of newborn stars numbering in the 10,000s in the same small volume of space. There are clusters, like I said, in these spiral arms. There are also clusters right in the heart of the galaxy, including at the very center, right around the supermassive black hole, which is located right there. Stars are being born immediately around the supermassive black hole. And you have to imagine that this is a wildly different environment than where the sun is born. So one question that we astronomers are trying to ask and answer this very time with our current technology is, do stars form the same way in different environments? Do they form the same as the sun formed out here? Or do they look wildly different as a result of some of these very extreme environments? To ask and answer this question, we have to first know a little bit about what we know about star formation. How does a single star form? Well, the very first step in star formation is you have to have some gas, and that gas has to be cold and molecular. So you start with something known as a molecular cloud. And when that molecular cloud gets pressed a little from the outside, it begins to collapse under its own gravity. So you see this cloud is plummeting into the middle, all the materials funneling in. As it continues to funnel, you will start to produce a protostar. The star hasn't ignited, it's not fusing hydrogen yet. So it's not really burning, but it's very, very hot inside. And you also get a disk, which will eventually become planets, we'll get to, and sometimes you get outflows of material as well. That protostar continues to collapse more slowly, and eventually hydrogen ignites. It becomes a bona fide star. You get disks and outflows, and then the disks gradually morph into and collapse into forming planets, and you get protoplanets. And then eventually the system settles down and looks something like the solar system that we know today. I see a question way back in the back. Typically, molecular clouds have some small twist or angular momentum associated with them. And when you have a round cloud collapsing that's also rotating, it turns into a disk. Okay, so now this is what we know. A star by itself from an isolated cloud turns into a star and a solar system. And not all stars form the same. We know that stars are born with different masses. There are stars that are born that are extremely massive. They're hot and blue in color, typically. And then stars are born very low-mass stars, much smaller than the sun. And these stars are low-mass, cool, and red. The sun is a nice yellow G-type star. Ignore the letters for now, but it's somewhere right in the middle. So one of the interesting things about star formation is how many of each type of star is born. How many very, very massive stars are born, and how many low-mass stars are born. This is known as the distribution of star masses, and this is a key way for us to understand star formation. If we can measure this distribution, we can maybe say something about the physics of the gas that the star is formed from. In particular, we see some interesting features. First, there's a peak around a third of the mass of the sun. This tells us that the physics in the gas make it so that clumps form around that size, and then those clumps turn into stars of about that size. You can see that the star formation process is less efficient as you go up to high-mass stars. You have far fewer of them, and similarly with low-mass stars. So it turns out that the sun is not the most common type of star, but it's not too far off as well. 10 stars 10 times the mass of the sun are far, far more rare than a solar mass type star, for instance. So we learn a lot by just counting up the number of stars and counting up how many of each mass there are. That tells us a lot about the physics of the cloud that they formed from. So if that's a useful proxy, this distribution of star masses, we could go and look at a lot of different regions and ask whether that's the same in all the different places that we look. And it turns out it is the same in all the different places we look, at least locally. Remember that red box that I showed you earlier? All of these measurements of this distribution of star masses have been done in that little red box. And for the most part, they all have the same slope on this high mass end, and they all peak at about the same position, at least within our ability to measure. So it appears that star formation is the same everywhere. But again, remember that little red box. Okay, so if we want to understand whether star formation is the same in these other more exotic environments, in these very massive clusters or around supermassive black holes, we'd like to do a very simple experiment, at least conceptually simple, We'd like to measure this distribution of star masses in all of these other very massive clusters and in the center of the galaxy, and just very easily compare them to something like the Orion Cluster, which is nearby and very well studied. So let's do it. Let's go straight into the most extreme environment we can possibly think of in the Milky Way. Let's go to the galactic center. Seems simple. Observe those stars, count them up, count their masses, measure their masses, make this plot, and we have an answer, right? There's only one problem. Well, there's actually more than one problem, but we'll get to that. The first problem is that we can't see the galactic center with our eyes. Optical photons do not reach us. Well, 1 in 10 billion photons coming from the center of the galaxy reaches us here in the Earth. And that's because we're in this Milky Way galaxy. And when you look up in the sky, what you see is that dark band across. That's actually the heart of the Milky Way. All the gas and dust that lies between us and the center of the galaxy is absorbing all of those optical photons, and they never make it to us. But no fear, there is a solution. We can switch to a different wavelength. We can look in infrared wavelengths. At infrared wavelengths, fortunately, only 1 out of every 10 photons makes it to us, but still that's enough that we can actually detect stars in the center of the galaxy. You can see from this infrared image, now we have a very clear view of the center of the galaxy. And we can do our experiment. So all we need to do is observe the galactic center in the infrared, and we should be done. Okay, well, what does the galactic center look like at infrared wavelengths? This is a picture from a 1.3 meter telescope, the 2-mass experiment. They did an all-sky survey and took beautiful pictures of the entire sky, including the center of the galaxy. This is about 2 degrees on a side. Now I want to set up an analogy for you because I'm going to use it for the rest of the talk. The size of this image is, imagine you had a geosynchronous Earth viewing satellite looking down on the Earth. This would be about the size, you'd be able to see across this, the size of Kauai, for instance. That's how big this is. So let's zoom in a little. All right, so now we're starting to see something interesting. We can start to see the individual stars. This is now, across this image, you can see, separate out the Kona airport from Kona town proper. And you can see the individual stars, so we're doing well, except that the center is still pretty blurry. So let's take another step. Let's zoom in again. Okay, here's the best image taken from this 1.3 meter telescope in the infrared. And you can see it's nice. You can see some individual stars out here, but in the very heart, it's just one big blurry blob. And you can't count up the individual stars because you can't see the individual stars. And here across this image, now we're talking about sort of seeing the size of Waimea, for instance. So what can we do? What do? We need a clearer picture to be able to count the stars in the galactic center. Well, if you're familiar with cameras at all, you may remember that larger lenses mean you can see more detail. So what we really need is a larger lens. We need a bigger telescope. Luckily, they exist. They have been built. We have the Keck telescopes, which we can now use, point them at the galactic center, and get a crystal clear view, except for this pesky Earth's atmosphere that we live in. I mean, we're all very thankful for the Earth's atmosphere, so we can breathe, but it does some nasty stuff to our pictures, our beautiful pictures of the heavens. Those photons that are coming from the galactic center, they travel so far, and in the last 30 microseconds of their journey, they encounter the Earth's atmosphere, which is turbulent and messy and completely distorts the wavefront of those photons. If you take a picture of a star and take it very, very fast pictures of that star, this is what you see. You don't see a nice, clear point source of a star. You see this messy, speckly pattern that's going, and that's all because of the Earth's atmosphere. Those photons that are coming in, they go through the stratosphere, and they go through these wind flows that are moving through our atmosphere, these wind layers. They hit the layer right above the ground, which is especially turbulent. Then they come to our telescope. So what can we do? Never fear, we are very creative. We've come up with a way of counteracting that turbulence from the Earth's atmosphere. This is called adaptive optics. So we put an adaptive optics system on a big telescope to try and get back to that above the atmosphere view. The way adaptive optics works is you have a wavefront of light coming in, and it's all crinkled, like a crumpled piece of paper due to the Earth's atmosphere turbulence. We want it to be nice and flat. When that turbulence comes through, normally we bounce it off mirrors and it goes into our science camera and we get this blurry image. But if somehow we could know exactly the shape of the crinkles, we can put something called a deformable mirror on and exactly reverse those crinkles and make a nice flat wavefront and produce a sharp image as a result. The way we actually measure those crinkles is using a star. We say we know the star should be flat, we measure how crinkled it is compared to what it should be, and we put those corrections right on that deformable mirror and fix it up so that it's nice and clean and flat again. The important things to note here is that you need a star. That star typically has to be observed at optical wavelengths. So we're back to that same old problem. We don't have optical stars to guide on in the center of the galaxy because we can't see anything through there. So what do we use for an optical guide star? Well, if the universe doesn't provide one, we'll make one ourselves with a laser. It turns out there's a very nice layer of neutral sodium about 90 kilometers up in our atmosphere. If you shine a laser tuned to the right frequency right up there, you can excite those sodium atoms and they will shine and glow and turn into an artificial star. And you can use that star and its light that comes back down to the telescope to measure the turbulence, put your correction on that deformable mirror, and get nice clean images as a result. So we should be all set now. We have our big telescope, we have our adaptive optics system, we have our laser. Never mind that this took 30 or 40 years to develop, but it's all there now. Let's do it. Let's point to the galactic center. This is a run that we had this past summer looking at the galactic center using the laser guide star adaptive optics system at Keck. In fact, we were using both laser guide star adaptive optics systems at Keck pointing towards the galactic center at the same time. But as you can see from this spectacular image, we shine our lasers up there, we get back our beautiful images. What do they actually look like? They look like this. This is what you would see if you didn't have that beautiful AO system, even with a big telescope like Keck. This is what you get when you turn on the adaptive optics system. Pretty spectacular improvement. Here, these areas here, they're just blurs. You can't see any stars at all. You couldn't count a star even if you wanted to. Here you can see there are hundreds of stars just in that small little area. Now we're getting somewhere. In the galactic center, it turns out that almost all of these stars are young stars. So if we look at them, count them all up, measure their masses, and construct that distribution of star masses that we were interested in, what do we get? Well, we get something that looks like this. If you remember, we expect something that falls off as you go to larger masses, you have fewer stars that are very high mass. But this is what it is in Orion, in this red line. This is what we see in the center of the galaxy. So we see far fewer solar mass type stars, small stars, regular sized stars, than we do the big stars. Way fewer than you would expect from something like Orion. So this universal value that we know of locally doesn't apply in the center of the galaxy at all. Well, why might this be the case? Is there some physical explanation for why this should be? There are a couple. In fact, before we made these observations, theorists had run wild and they had predicted more high-mass stars, and then they'd also predicted fewer high-mass stars, and then they had also predicted it should be just the same as in Orion. So they had no idea. But now we actually have a constraint. So now we know something about physics. We've learned something new about the physics of star formation. In the center of the galaxy, when you have those molecular clouds that are collapsing, as I said before, those molecular clouds are experiencing very strong tidal forces from the black hole. Just as the Earth has tides due to the moon, these molecular clouds in the center of the galaxy, close to the black hole, will be pulled more strongly than away from the black hole. So they'll be pulled apart and tidally stretched. And if you're a small cloud, you can be tidally stretched so much that you just rip apart. So you can imagine small clouds just can't survive. Therefore, small stars can't form. And that's a pretty reasonable explanation for what we see. It's just that only the biggest clouds forming the biggest stars can really survive in this strange and extreme environment right around the supermassive black hole. So if we're keeping score, how does this extreme environment compare to something like Orion? Well, so far the galactic center is not the same as Orion at all. But it's got a supermassive black hole. That's pretty rare. Maybe this is just a crazy one-off, yeah, it's strange, but what about the whole rest of the galaxy? These other star clusters that are sitting out in environments maybe halfway between us and the center of the galaxy, what do they look like? Let's go and measure their mass functions. This seems like it would be an even easier problem in the center of the galaxy. It's very obvious where there's a big massive star cluster sitting there. There it is. So let's count up the stars. There's only one problem. Which stars belong to the cluster, and which ones don't belong to the cluster? Does this star belong to the cluster? I don't know. How do we tell? This has really stumped us for a while. How can we tell which ones are in the cluster and which ones not? Which ones do we count and include, and which ones do we throw out? Because they're just interlopers from the rest of the galaxy. Fortunately, stars move, and stars in a cluster move together. We can use that to figure out what's in the cluster and what's not in the cluster. That's great. We'll just measure their motions, count up the ones that are moving together, and those are in the cluster. All right, so let's do it. Here's the images. Can you see which ones are in the cluster? Can you see them move? No. Okay. What if I show you a plot like this? This is now the motion vector for every star in that image that I just showed you. Can you see which ones are in the cluster? Can you see there's a cluster? There are a lot of motion vectors moving the same way. So it's there, it's there. We just need a better way of visualizing it. So if you take each one of these little arrows and you measure its length in this direction and in this direction, put that on a plot. Now you can see something that starts to look interesting. This is the motion in the x direction and the motion in the y direction. Each point is one star. And you can see there's a whole lot of stars that fall together. They're all moving the same way. That's the cluster. This is the Arches cluster in the center of the galaxy. It's near the center of the galaxy. You can see the cluster very tightly clustered in motion space. And then there's a whole bunch of contaminating field stars that are in front of the cluster, behind the cluster. They happen to be within your field of view, but they don't have anything to do with the cluster at all. But you can see how great this technique works. There's the cluster, get rid of everything else. Now we can really measure the mass function. The same thing works for the clusters in the disk of the galaxy that are a little bit closer to us as well. Here you can see every star and the stars that cluster very tightly together in this motion plot. That's the cluster for Westerlin 1, another massive cluster in the disk. Okay, so now we can measure mass functions for these clusters as well. Once you've actually identified the cluster members, which are these ones that are tightened up in this motion space, you can look at them in a plot of brightness versus color. And remember I said hot massive stars are typically blue, low mass stars are typically red. You can use their brightness and their color information to measure their masses. And once you have their masses, you can make their mass function. So what do we have in terms of the final answer for these other clusters? They're not so extreme as being around a supermassive black hole, but still far different from our local environment. Well, what we found out is that while the galactic center did not match Orion, the Arches cluster did not match Orion either, but Westerlin 1 did match Orion. This is confusing. Here we had a supermassive black hole to fall back on. Arches and Westerlin 1, they're producing different answers. What's the problem? Aren't they the same? Well, if we go back and look at that picture of the Milky Way and where these clusters fall, here's the center of the galaxy. That red star there was the central cluster that we first looked at. Here's the Arches cluster, very close by, so it's still in a very inhospitable environment. It's far enough from the black hole that it doesn't really know about it. But there are so many stars, and the whole region is very hot and turbulent, so it really is quite different in here than it is out here in the spiral arms. So maybe that's the explanation. Maybe the Arches cluster, which is in this central region, experiences enough differences when it's a molecular cloud, when it's just a baby, that it looks like it produces a lot more massive stars than low mass stars compared to Orion or something like Westerlin 1 even that's out here in a spiral arm. This is only a sample of 2. We have 1 yes, 1 no. We don't really know what the answer is and exactly how to tie that back to the physics. Fortunately, those are not the only massive star clusters in the galaxy. There's lots more we can do. This is a face-on view of the galaxy, just showing the spiral arms. And all these colored points are other massive young clusters that have been discovered just in the last decade or so. So there are quite a few, and we can study all of them eventually, if we can. But our current AO systems have a few limitations. So I wanted to talk a little bit about how we might go about looking at the rest of these population, really making headway in terms of understanding how stars form in these extreme environments. So let's talk about the future. The future is bright from sodium lasers for adaptive optics. Here's the 2 lasers now at Keck. There are lasers popping up all over the world. But in particular, I wanted to point out here is one that has multiple lasers. So that's going to be interesting. I'll tell you a little bit more about that in just a moment. But let's talk about what the shortcomings are for current adaptive optics systems. This is a picture of the Arches cluster that we put together from Keck with adaptive optics. And you can see it's not like those nice square images I was showing you. The way we actually did the observing was to build up tiny little patches and then piecemeal them all together. And that's because adaptive optics systems, as they're currently built, have a very limited field of view where they can make that correction that we absolutely have to count up the individual stars. So it's hard. You don't even cover the whole cluster in a single pointing. You have to stitch them all together. It's very time-consuming and makes the process of measuring motions very hard. Fortunately, there are creative people who are coming up with ideas for how to get around this problem in adaptive optics. If you have multiple lasers shining up in the sky, you can measure the atmospheric turbulence not just towards the one laser, but in a whole cone, and that can improve your correction over a much bigger field of view. You can also put in multiple deformable mirrors on the backside, and that allows you to also correct for a bigger field of view. Let's look at what that actually does to our images. Here's a picture that shows no adaptive optics, quite blurry. Nobody wants to go back to that. Here's what we have today. Here's a classical adaptive optics, laser pointed right in the middle. You can see you get really good images in this little tiny patch in there, about 10 arc seconds on a side. That's 10 or 20 arc seconds. That's the useful measure. So you can see just very small right around the laser. Now, if you put in multiple lasers or multiple deformable mirrors, here you have 5 lasers here, you can expand that almost by a factor of 10 in terms of useful field of view. That makes you 10 times more efficient in observing. It makes your images cleaner as well. So all around, it's a good thing. And these systems are being built on on one telescope, but we need them on more telescopes as well. What else can we do? Well, this is what we can do on our existing telescopes. We can build fancier AO systems, adaptive optics systems. We can also just bite the bullet and build a bigger telescope. That would be great. Today we have 10-meter telescopes and a host of smaller ones, but we could dig deep and build a 30-meter telescope. Or in this case, there's 20-meter telescopes being planned, 30 meters and 40 meters being planned. So what does a bigger telescope get you? Bigger telescopes get you better resolution, and when you have better resolution, you can also measure smaller motions, both of which are really good things in terms of star formation. If we could get up to a 30-meter telescope with a good adaptive optics system behind it, here's the kind of thing that we might be able to address. This is a simulation of a star-forming region. Simulation, not observations. I wish it were observations, but it's not. In someone's computer, they've put in some code for what we think about the physics in star-forming regions. You can see gas clouds collapsing. Notice they don't look like those nice balls of gas I showed you earlier. This is real messy gas that's turbulent and filamentary. It's all collapsing to form stars. But what I really want you to notice is the stars are going wild. They're moving in all different directions. There's lots of things that we could learn about how stars are forming if we could just measure their motions internally within that cluster. Not just the whole motion of the cluster itself, but are we seeing lots of stars being ejected? Are we seeing lots of these filaments? That's really where we'd like to go with bigger telescopes in the future. What we would love to have is a real observational data set that we could compare directly to this kind of simulation. Today, we don't have that. And those motions are easier to measure if we have more stars and we have better resolution. So this is just a little animation showing you where we are today with current AO. That's a small example of what you can observe. And if you had a 30-meter, you can see how many more stars, and you can see it's very easy to measure even slow-moving faint objects. So there's a real advantage to building a bigger telescope, getting better resolution, and measuring tiny little motions to measure what it's doing inside the cluster, and really get a handle on how stars form. Mm-hmm.
Are these stars in orbit? They appear to be in orbit.
So this is just a picture of the stars right around this black hole.
Have you been able to follow them to see if they follow a path, or are they just randomly flipping around?
This is centered right on the supermassive black hole at the center of the galaxy, so most stars orbit the black hole. In the galaxy at large, stars are going around, including our sun. We go around the galaxy happily. But
there's no fixed pattern.
That's right.
Patterns forming.
That's right. Except you can see the spiral density waves going through and things like that. We don't see it in the star kinematics. That's seen in gas. Mm-hmm. Oh, hold on one second. Have one in the middle. Can you say that one more time? I just didn't hear you. Can you ask your question one more time?
They don't look like they're orbiting in a galactic plane.
As you go deep into the center of the galaxy, they don't know about the galactic plane. The galactic plane is hundreds of times, well, thousands of times the thickness of this image I've shown you.
It's no longer flat.
In here, it's just round. They think they're round. If you go out far enough, in fact, there's a bulge in the galaxy, which is just a nice round part in the middle. Back here. The one that's orbiting here very quickly, that star is about 10 or 20 times the mass of the sun. Most of these other stars that you're seeing here are also very massive, 3 to 6 times the mass of the sun. Low mass stars are there. That's all the new stuff that will get picked up by a bigger telescope. Right now, we can't see deep enough and with enough resolution to pull out the low mass sun type stars. Mm-hmm. Maybe, we don't know. I mean, all we know is what we know from Orion. Yes, there are low-mass stars. Exactly. Whether they can form here or not, that's a big open question that we don't have an answer for yet. They can certainly form in the outer galaxy, and they may be ejected or shot in through random processes. That would be a small number of stars, but they could be there. We do know there is some lower mass stars, maybe solar mass stars, a little bit further out. We're still trying to determine whether they go all the way in or not, or whether they just kind of hang out, and if they make it in, they get disrupted very easily or kicked back out. All right, so I'll just close with one final image and say the future is bright for adaptive optics and for studies of star formations and regions outside of our local neighborhood. We have a beautiful view of the Milky Way now, very sharp and focused, and lasers and adaptive optics and deformable mirrors are really helping us. We're still in our toddler phase. We've got new first-generation AO systems for the most part, and second-generation new technologies are being put on telescopes today. But we still have a lot of distance to go, both from the technology and the science standpoint, to really understanding how stars form, not just around the sun, but throughout our galaxy. Thank you.